Hey, I'm Robert. I'm one of the co-founders and CEO of Anyscale.
And I'm Goku, and I work on machine learning here at Anyscale.
We're going to talk about solving some of the core infrastructure challenges for building LLM and generative AI applications. A lot of the stuff that we're going to show you today is based on Ray. Ray's an open source project, started out of UC Berkeley. It's been used by companies like OpenAI to train GPT-4. It's being used by companies like Uber and Pinterest to run all of their deep learning. So this is really starting to be the heart of scaling AI workloads at a lot of tech companies. And really, that is spanning the spectrum from getting started on your laptop, writing your Python script, all the way through the most cutting-edge foundation model use cases out there.
Yeah. I've heard about Ray actually since 2019, which is, I guess, half a decade ago now, and it's amazing to see kind of the adoption behind it.
Go, could you want to talk a little bit about some of the challenges around actually that teams face when doing AI and trying to build AI applications and get them in production?
Yeah, I mean, regardless of what kind of machine learning application you're trying to build, whether it's more traditional deep learning or LLMs or Gen AI, two of the most important factors here are velocity. How quickly can my team move? And actually doing things at scale.
Yeah, and how quickly your team can move is also related to how quickly the individual developers can move, right?
Absolutely.
And we've seen a lot of obstacles to moving quickly as an AI engineer, because you're hired to do AI and to build AI applications, but a lot of these people find themselves having to manage clusters, right? Having to scale workloads, having to think about GPUs and other hardware accelerators, right? And these are thinking about how to move from development to production. There can be a lot of challenges.
Exactly. Yeah, you're not just on your local laptop anymore. In fact, these models just won't fit. So thinking about kind of scale is something that developers are thinking about from day one, even in the development stage.
Yeah, I mean, scale is just a fact of life, and if you're only scaling, to your point, if you're only scaling in production and not scaling during development, then you have a different development and a different production environment, a different code base, different frameworks, and that increases the gap between what's running in development and what's running in production, and means that it's more likely that things will go wrong when you transition, and that there'll be a more expensive handoff between those two stages. Maybe a handoff to another team, a rewrite, or something.
Absolutely.
Like that.
That's actually where almost all the mistakes and errors happen. And I'm sure you've heard the quote, well, it worked in my laptop. Yeah, that's exactly one of the biggest challenges.
Yeah. Let's dive into data processing first.
So what we have here is kind of an overall diagram. This specific task you may recognize is kind of prepping your data for kind of filling your vector database for RAG applications. But I'm just going to use that as a kind of a skeleton of a data processing workload. And
there's a lot of different reasons you need to prepare your data. This could be preparing it for pre-training. It could be preparing it for fine-tuning. It could be even preparing it for some kind of batch inference task, right?
Yeah.
And of course, I want to say there's a lot of interesting challenges here. In fact, this diagram, in some sense, may be oversimplified, right? There's you have CPU compute, like some of the reading and writing and pre-processing. But it's often typical to have GPU compute as well, doing inference, embedding computations, and so on.
Exactly, yeah. You're going to want to kind of work with all different kinds of compute resources. And your data could be anywhere. It could be in your local system, cloud storage, data warehouses. And you want to be able to kind of read and write to all these different sources.
And actually, when you have mixed CPU and GPU compute, the challenges can get even harder. For example, you may want to scale the CPU pool of workers and the GPU pool of workers independently. Right? It may be more CPU or more GPU intensive. You may have a batch size may be appropriate, like different batch sizes may be appropriate on the CPU versus on the GPU.
And we'll see all this in action, where kind of per workload within the data processing cycle here, we'll have full control as to exactly what kind of compute strategy I want to use here, and do it in a way where we're not actually maintaining the infra ourselves and connecting these different devices together. We can just focus on the actual code that we want to develop.
And you mentioned that you may need to scale during development. Can you say a little bit more about that and some of the challenges of scaling during development and really creating a good productive development experience for data processing?
Yeah, so obviously if your data lives on a single file, you're not really thinking about scale. You can kind of have it on your local laptop and it just works. But now when we're talking about, even during kind of this experimentation development phase, we have very large data sets. I'm not even going to get to the models yet, but just large data sets, let's say living in cloud storage, like an S3 bucket or something. It's impossible to just kind of read from there if it doesn't fit in your one machine, right? Let alone actually doing the processing and then being able to write that again back to like cloud storage. Yeah. So these are things that actually won't fit in memory.
Yeah, and you want the ability to be able to select different sizes or different portions of data, right? You often want to be able to try running something with 10 data points or 1,000 data points or 1,000,000 and be able to go back and forth between them, run at different scales.
Yep. Yeah, the same kind of traditional principles of doing machine learning, for decades still holds here. You still want to kind of try it out on a small chunk first, but you actually want to be able to apply that at scale to your entire data set, especially before fine-tuning.
And even though you're doing this at scale, the same usual principles of software development and debugging are relevant, right? You may run something at scale on on 100 machines, and then find out you forgot to import some Python library. You need to install some extra dependency, right? So you pip install it. Of course, you pip install it. You need to get it on all of those machines and make sure it's there, so it's not. And if you don't have a good setup for doing this, you're running SSHing to 100 machines and running pip install on all of them, and you're going to run into a lot of challenges, right? These are the kinds of things that Anyscale features like Workspaces really just solve out of the box. You just pip install it once. The same environment's going to be present on all the machines. You can do that interactively at different scales.
Yep. We'll see Workspaces in action where kind of just focus on our code and environment, and we just have kind of this seemingly infinite compute underneath that we'll leverage.
It's also important to have a good IDE story, right? A lot of people like developing in VS Code. What does that look like in the distributed setting if you're running on a cluster, right? You want to be able to integrate that development environment with your IDE so you have the same familiar development environment. You can set breakpoints, you can step through the code, even if it happens to be running, it's backed by a cluster and running across a bunch of machines. Again, these are the kinds of things that we've built into Workspaces and really move the needle for just overall developer productivity. And really dynamically configuring the cluster is important because the last thing you want to do is get all your dependencies installed, set everything up just right, scale the cluster, run your application, only to figure out actually you used the wrong instance type. You need a different instance type or the wrong type of GPU, wrong hardware accelerator. And then you have to tear everything down, spin up a new cluster, reinstall everything. We've all been there.
Yeah.
And that's exactly what you want to avoid.
Or the other side, what a lot of data scientists and machine learning engineers do is get the beefiest machine possible and usually have some questions to answer to your infra and platform team on why you wasted so many resources. So Workspaces is great to just kind of start with a nice, lean, simple head node. And then as I need to kind of use it for different workloads, like large-scale data processing or kicking off a fine-tuning job, it runs a separate workload, and those workers work on that specific task and then scale back down to zero. So kind of just very efficiently using this compute only for the workloads that it needs to actually have it available for. First off, Robert, we're going to jump into kind of data processing.
Let's do it.
And obviously, we're going to be talking about everything in the context of a specific task because I always think it's great to actually learn about things by looking at code that works. But just know that obviously all of this can easily translate to different data modalities, different types of models we'll look at, and just kind of any kind of machine learning workload.
So what task do you have in mind?
So today we're going to start off with a pretty popular data set. It's called the Vigo data set. So first thing I'm going to do is actually just load this data. So this is available through Hugging Face, and I'm going to have it locally available. Obviously, it's a tutorial where I don't want to spend too much time kind of loading data from large sources, so we picked a data set like this.
If you did want to load a larger data set, you'd be in a good position to do it.
On here, absolutely, right? Because we don't think about it as kind of one machine, but I can now read data and have it chart across multiple workers.
This looks like a regular notebook, but it's actually backed by any size cluster that you want, any kind of compute resources. If you need a ton of GPUs, a ton of other compute resources, accelerators, it's right there.
Exactly, yeah. So this is actually, the Workspaces on Anyscale, and I'm showing you the VS Code here because that's my kind of preferred IDE. This is, in fact, a notebook running in VS Code, but you have options to choose kind of between a Jupyter Lab experience, a terminal as well. And as you mentioned, this feels just like my local laptop here, but if I go here, I've actually started this workspace on top of compute that is actually running on cloud. So I've picked a head node that has 8 CPUs and 32 gigs. And we'll talk about kind of what else is available on top of this when we need it. But right now, that's all I'm using. It's a kind of a very lean machine that I'm running this on top.
And that's exactly what you want. If you're not running intense computation, you don't want a lot of machines started up. But I like the look of this auto select worker nodes button.
Yeah, we'll take a look at that in just about a second. Okay, so I've loaded the data set, and just like traditionally dealing with data sets, I'm going to go ahead and split it. So this comes automatically with a train, validation, and test split. Let's just look at a sample here. What I want to focus on is kind of the inputs and outputs. So here, this is a data set that has something structured. So it starts with an intent, then it extracts a bunch of entities. And then the output actually for this data set is a very unstructured sentence that's composed using these structured inputs. Now, what I'm going to propose is actually we flip this. I actually want to have this unstructured sentence as the input, and let's see if we can leverage large language models to be able to extract this structured information. And, everyone kind of talks about LLMs and kind of this generative space, but this is kind of an example where it's going kind of back to structured. And we've seen a lot of our customers and kind of the world, frankly, a lot of these applications were reserved for traditional deep learning. But now people are leveraging LLMs to do the same because first, they can get away with having far less data to actually have very performant models. And number two, a lot of other perks like open domain. The LLMs have a lot of kind of underlying knowledge that they can leverage to do tasks like this.
Yeah, actually, that's a good point. We often think about LLMs and generative AI really favoring unstructured data over structured data. But I think one point that people sometimes underestimate or miss is that the potential for generative AI and LLMs to really make it easy to create structure from unstructured data and actually lead to way more structured data.
Absolutely. Yeah. Awesome. So before we can actually use this data to start fine-tuning a model, there's a couple pre-processing steps we want to take. And I'm going to do this, start with Ray right now, because even though this data set is small, we want to be able to extend this to a data set of any arbitrary size. Yeah. So first thing I'm going to do is actually import Ray and wrap this data set with Ray. Now here the data set's already in memory, but this could be done with something, let's say in cloud storage as well, where I can kind of read data from cloud storage or any other source and have it be able to be sharded across workers.
And a typical place to store your data might be a cloud storage like S3,
exactly,
or Google Cloud Storage, or a Databricks or Snowflake. There are many different options there.
Exactly. Okay, so once I've loaded the data set, kind of works very similar. I can kind of take a look at the data. You can see what the data point actually looks like. And I'm going to prepare a couple small functions. So thinking ahead a little bit here, but to actually fine-tune our model, we need our data set to look a certain way and follow a certain schema. And this is actually very similar to how everybody does fine-tuning these days. OpenAI follows a very similar standard. And I'm going to wrap this into a function called preprocess that'll just kind of apply this schema to all of our data points. Now, this is a system content here. I'm basically telling the LLM kind of how to behave. And because we do want structured outputs, I'm kind of telling it first, predict what kind of intent that we want, and then extract these kind of different types of entities. And the output can basically have a subset of these types of entities.
Makes sense. And of course, this is specific to the particular task we're trying to do right now.
Yes, exactly. So far, if you looked at the functions, everything's in pure Python. And to actually apply this at scale, I don't really have to do anything crazy. All I'm going to do is take my function, it was called preprocess, and we have our data set, train DS here. And I use this function from Ray Data called map batches. And I can simply take the data set and apply this function on that data set. And I can specify things like any function arguments, and our documentation has a lot more, but we can even specify different compute strategies. How many of what device type do I want to use?
Nice.
And you really want to do that to be able to have full control over what resources do I want to spend on this, how much is it going to cost me, et cetera. Yeah. And now for the really cool part, Robert, when we actually run this, this is no longer running just on this head node right here. So because we've enabled this auto select worker nodes, based on things like my data size, the workload that I'm actually running, the compute strategy we specified, and in this case I'm using the default compute strategy, the appropriate number of worker nodes actually get spun up. They work on this workload that we have, and then they scale back down to 0.
That's incredible.
Yeah, and you can see kind of there are a lot of logs that come out of this, and we get to see at the end. I'm going to take a sample, and you can see that it's actually has successfully applied that preprocessing function on all of our data.
Wow.
And then I'm going to actually just do this for the other data splits as well, because we're going to be using it later on. And then finally, I'd love to just save this data. I've already gone ahead and done this so that folks can easily access this data. But once it's there, you can easily read from that cloud storage as well. And something convenient that Workspaces comes with is that every workspace has kind of a default cloud storage and even shared storage as well if you're working with a group of folks. But it's just very convenient to be able to save your data to various, not just data, but any kind of artifacts to storage and be able to retrieve that later on.
Totally. And that is one of the challenges with distributed computing in general. Is like, okay, I ran my application. It's on there's some artifact that was produced. It's on some machine somewhere. Maybe I saved it to disk, but like, where is it now? And if I need it on another machine or in the next job that I'm running, how do I get it? How do I hand it off between different pieces of my application? So just having a clear, consistent story for storage and producing artifacts and using them downstream, that's huge. Awesome. Thanks for walking us through that notebook.
Yep, and now we'll put it to good use.
Awesome.
All right, Robert. So now we're going to leverage the data set that we pre-processed and actually use it to fine-tune some models.
All right, let's do it. This is the fun part.
All right. So before we kind of get into fine-tuning, I did want to make it clear that traditionally we wouldn't just jump to fine-tuning. We'd want to actually experiment with some base models and actually evaluate those base models to see what we're working with.
Yes, I mean, the whole point of fine-tuning is to improve the model quality, right? So if you don't have a way of comparing the quality, evaluating the quality of the fine-tuned model and saying, hey, this is better than the base model, you're not going to know what to do with that.
Exactly, yep. Now, for fine-tuning, there are a couple different methods, and we're going to talk about both of them, but the two popular ones are LoRa and full parameter. And on Anyscale, we actually have a couple different recipes that are available.
And of course, we're going to allow you to do both.
Exactly, yeah. We have got a couple different recipes inside this training configs directory, which comes with all the workspace templates for fine-tuning. And these are basically recipes that the community has really worked hard on and pulled together every time a new model comes out. And it comes with a set of kind of default configuration options that just work for this specific model. And we've exposed all these recipes, and of course you can modify all of these different values as well. And you have full control in terms of like what exactly you want to change and what you want to experiment with.
Yeah.
Now, the one thing, we're going to go through a few of these. The one thing you definitely want to change is the train validation path, especially if our users are experimenting with their own data sets. So I've gone ahead and changed it to the cloud storage locations that we've saved our data set to. But then, the rest of the parameters, we'll look at a few that are kind of model specific, context length, for actually how do you want to actually train this? So I'm setting the number of devices here, number of epochs you want to experiment with.
And the fact that you can just change the number of devices from 16 to 32 or whatever you want and use more GPUs and have it run faster, that's awesome.
All right. So after this, you can kind of play around with more traditional parameters like learning rate, what kind of padding logic you want to have, how many checkpoints you want to save. By default, we kind of save the best and the last checkpoint, but full control over that as well. So a couple more interesting configurations here. We have Deep Speed, which is another open source library that we leverage. And the community has really worked to kind of make it really easy to do things like distributed training, mixed precision, checkpointing, gradient accumulation, all these kind of different things that are really important for training. But as a developer, I don't really want to think about that kind of managing those aspects. I want to focus on my training logic and actually just work on the model itself. Our team here, as well as the community, they're always working on the next set of optimizations to enable for these kind of workloads. So we make sure that's available also through these configurations, things like flash attention, and it's guaranteed that we kind of stay on top of this as well and keep enabling that for our users. Now, in terms of kind of the compute strategy, you again have control. You chose a number of devices or workers that you want. You can also choose kind of the accelerator type and things like that, and we'll see that in action when we actually run off the workload. And now for actual fine-tuning logic, we can either change the entire set of weights in our model. It's called full parameter fine-tuning. Or we can do something called LoRa, which stands for low rank adaptation. That's really a great strategy if you want to not tweak the entire set of weights in the model, but really kind of develop these low rank matrices and alter those weights instead of the original set. Learnings from our customers and our internal applications, you always want to start with LoRa. It's just kind of a simpler, faster way to kind of fine-tune. And then based on your task and what you're learning from these, you'll want to open up full parameter.
And full parameter fine-tuning will be more powerful.
Absolutely.
But they're both great techniques.
Yeah, exactly. And of course, you have full control here as well. You can obviously control the ranking, some other kind of parameters in terms of the actual weight matrices and the training logic as well. Awesome. So with these configurations, you have full control over these. And to actually launch this job, we have a script here that takes in this configuration and kind of the compute strategy that we have, and it just executes this. So now, because we've enabled this auto select worker nodes, our head node is still this lean machine right here. But when we kick off this workload, it automatically provisions the appropriate workers. This workload executes, and then these workers scale back down to 0. So when this is actually running, the appropriate workers will be kind of provisioned and executed there. And we have a fantastic Ray dashboard, which gives kind of full observability and full view into what's actually happening. And we get to see our GPUs go burr here. So GPU utilization, CPU utilization, what's happening on the disk, and then obviously what workers are actually provisioned. It's just a great oversight to actually see what's happening under the hood, and make sure that training's properly happening.
When you're debugging or building these types of applications, there are typically two types of things you're trying to debug. One is just correctness. Like, is the thing running? Is it crashing? If it's crashing, what's the error message? And that's one type of monitoring that's very important. But another is about performance, right? So it's running, it's correct and everything, but the question you're asking yourself is, why isn't it faster?
Yeah.
And in that case, you really need to know what different resource might be the bottleneck, whether that is GPU utilization, GPU memory, disk space, many different things like that. And having those metrics across the cluster at your fingertips is essential.
So once this is actually done, it's one of the most frustrating things for me is that I run, let's say, a large workload like this, and then I have my code fail on the actual checkpointing piece.
Yeah, that sounds frustrating.
And I'm going to have to restart. So again, as I mentioned in the previous template, Workspaces comes with a default cloud storage location. You can use that or anything else that you want. But now our models and kind of key artifacts are automatically stored for us. So things like the actual checkpoints, the best one, the last one, the results, these are all automatically stored in the default cloud storage. And now I can access these for kind of inspection and other workloads.
That's brilliant.
Awesome. So here I'm just going to quickly show what that looks like. This is the default cloud storage. I go ahead and extract these from cloud storage. I pull them locally. And then I just visualize, for example, our result.json file. And again, if you have TensorBoard or other integrations, you can also visualize these things there. I'll show what it looks like to actually pull up the checkpoints and now use it for evaluating this model because we need to actually see that it worked.
Excellent.
All right, Robert. So now that we fine-tuned our model, we're actually going to see if it worked. Now, so far, when we actually did the fine-tuning, we had a metric out of the box, and it's typically perplexity, and you can alter that as well. But perplexity, while it's a meaningful metric, and it's really kind of based off of how perplexed the model is at kind of seeing a new token, it's not going to be, in most scenarios, it's not going to be representative of the underlying task. For example, in our scenario, we're wanting to go from an unstructured sentence and extract structured outputs. I'm sure we can think of a lot of different ways to evaluate this, but kind of picking a random distance or entropy-based metric isn't going to be truly reflective. So to get started, we're going to be setting up Ray again. We're going to have a Hugging Face token here that will pass, and we'll use this to actually load our base model. So far, we jumped to fine-tuning a model, but I also want to do evaluation on the base model just to see what it looks like.
Makes sense.
All right. So I'm going to load our data set that we had. And if you recall, we actually we created a test set as well. Now, the model did not have access to this, which was very important. We had only saw the train and validation. Awesome. So once we have our test set, I'm actually going to separate it into inputs and outputs. So just to recap, the inputs here are going to be that system and user content that we had before. And then the outputs are going to be the actual structured outputs that the LLM hopefully also generates. So just to look at that, here's one example. I'm going to actually also load a tokenizer. So if you recall, the model that we ended up fine-tuning was this Llama 3 8B, the instruct version. I'm going to load the tokenizer from Hugging Face. And the reason I want to do this is because there's something called a chat template. So during fine-tuning, what we had done was we obviously created our data set and we pre-processed to fit a certain schema. When that's actually being inserted into the model, that piece of text is actually templatized. So the LLMs during preprocessing for the LLM itself, it'll add some special tokens like a beginning of sentence token, end of sentence token, and we want to make sure that we apply the same template when we feed the data from our test samples into our same model. So this is exactly why we need the tokenizer. And what I'm going to do is load one of the model artifacts from our fine-tuning run. So from our fine-tuning...
Which model artifact?
Yeah, so inside, from our fine-tuning, the model artifacts that were stored in cloud storage, it basically just saves all the artifacts in one location.
Perfect.
And inside this bucket, there's a file called tokenizer config. And inside there's an attribute called chat template. So very simple. I just load up the chat template, and now I can actually apply that chat template to all of the examples in our test set.
That's fantastic.
So this way, I can now have the same inputs be available for basically offline inference for our models. Okay, so now that I have, here's a quick example. So this was originally just the input, and now we've added, kind of applied the chat template to it. Okay, awesome. So from this step here, we're actually going to kick off batch inference. And just to kind of recap here, evaluation is one of those tasks that's really ripe for batch inference because you have a set of, let's say, a large set of inputs. You have a model, and in this case, it's a very large model. I don't want to feed this one at a time. I want to take the entire batch because it's available right now, and I want to be able to feed it to my model and look at the entire set of outputs.
Yeah. And this is just one example of many different types of batch workloads that you may come across. You do batch workloads for evaluation. You may also want to do it for just processing a large amount of data. You have earlier on, we talked about taking unstructured data and producing structured data. Mm-hmm. It's a very natural batch task to perform on a large data set that you collected.
Absolutely. And if you recall before, when we applied map batches from Ray data, we had applied a specific function to our entire data set. This is a great time to show how this offline batch inference, we can actually follow very similar logic, same map batches function, but instead of a function, we'll actually pass in a class.
Yeah, so why a class this time?
Yeah, so in terms of like what we actually want to, the operation we want to apply on the data set itself. So in our case now, we took the test data set, we've applied the chat template, and now I want to apply this class because there are certain attributes that I want available for every kind of operation on this data set. So for example, here, the class itself will have a couple pieces of information, the LLM, sampling parameters, which I'll talk about in a bit, and then kind of our LoRa path. These are things I don't need to change in between each function call, but they are pieces of information that I want to instantiate my class with. And then the class itself, the function that it'll be responsible for is under this call.
Yeah. I mean, so you're running the fine-tuned LLM on all of the data.
Exactly.
Right? Which of course is a function.
Exactly.
Right? Now, you mentioned there's this information you want to share between all of the invocations of that function, but I think part of the key is that information is kind of large and kind of perhaps expensive to initialize.
Exactly.
Right? And so if we were to do that repeatedly,
every single time,
it could be kind of bad.
Exactly. Yeah. So there's a very efficient way to apply our model basically to that data set. Awesome. So I've actually written this function. Again, going back to kind of really relying on open source. We're using VLM here, which is one of the most popular and reliable, well adopted inference engines.
Yes.
And you know, here at Anyscale, I think we're also
we actually contributed quite a bit to VLM.
Absolutely. And it's a fantastic library that's really matured over the last couple months now. And I'm leveraging it here to basically really easily switch between our base model and LoRa. So if you look at the actual call that's executing here, I have self.llm, and that uses the offline LLM class from VLM. And to actually generate the outputs, I just pass in my inputs, pass in sampling parameters, which I'll just cover in a second. And it's the exact same thing for if I want to generate outputs from a LoRa version. All I have to pass in is this LoRa path itself. So what's happening here is that for the base model, we have a base set of weights. And then for our fine-tuned model, which is LoRa, use the same base model set of weights and then just merges it with these LoRa weights, which again are saved from our fine-tuning run. So nice. It's as simple as passing in an extra path to use our fine-tuned model. Okay. And in terms of the outputs, again, full control here. I want to actually have access to the prompt. So what were the inputs that went in? what are the expected outputs, which is just, again, from the batch that were passed in, and then what are the generated outputs from this model. So I want all three pieces of information.
And so here, are you expecting the expected outputs and the generated outputs to be identical?
They should match. Yeah, exactly. Okay, so first let's go ahead and apply this for using our base model. So set the model. These sampling parameters here are kind of how you want the model to behave. Mm-hmm. There's a lot more parameters that you control here, but two that I care about right now are temperature is 0. And then max number of tokens. So this really, again, depends on which model that you use. But I don't want the output to, I know my outputs are not going to be too large. This is something you'll want to set if you want to kind of place any constraints on how large the output should be and where generation should stop, for example. Okay, so I'm going to go ahead and apply the base model to our data set. So it looks very similar. I have the test data set, and we've applied the chat template, map batches, and I just pass in the class. And now, just before, if you remember, we used the default compute strategy, where just allocated the number of workers for that job. But now I'm going to actually decide how many LLM instances that I want, how many GPUs per worker, and what is the batch size. And we can play with this based on what we care about. And yeah, full control here. And
so I love this. This is the fact that you can just pass in the class or the function.
Yeah.
Right. The fact that you can just specify the concurrency and the GPUs with a single number and the batch size. And of course, again, there are defaults for all of these things. But this is just, and then as a consequence, you can scale this across the same computation on all of your data across a huge amount of data, a huge cluster. Yeah. That's fantastic.
Exactly. And of course, you can play around with the accelerator type as well. Awesome. So I'm going to go ahead and I just want to look at a couple examples. So here's kind of the, I guess, bad part of using one of these base models for a complicated task like this. I feed in the prompt and you can see the expected outputs are, the intent and the different entities. Mm-hmm. But our model has never seen this before. And so the generated text is actually a very long story, which is very meaningless. In fact, if I actually print this, it's actually writing out a class for us. So it's completely kind of misunderstood the task. Yeah. And this is actually definitely expected behavior, right? We haven't done anything like prompt engineering here. Something we could have done to help the base model a little bit is maybe provided a few examples here, and that might work. But certainly just using the raw base model is not giving the right output. Next, we're going to actually do the same thing with our fine-tuned model. Very similar, and you'll notice the only thing that I'm adding here is the LoRa path. Mm-hmm. By passing in that, it now uses the same base model, merge the LoRa weights, and now same inference call happens. So let's look at a few examples here. You can see the expected output, and you can see the generated text is actually, in this case, exactly the same. Nice. But let's go ahead and do like a quick eval here. So I'm going to keep it simple. Let's be a little bit strict, so let's look at exact matches. So I just say any time that the expected output matches exactly with the generated text, count that as a match. Obviously, you can do many different metrics here. Recall, you can be a little bit more lenient, completely up to the user. But I just wanted to quickly show the effectiveness. Even with this strict evaluation, there's almost a 96% match here. Wow. Which is great to see from just like I think a few epochs of this as well. The last thing I just wanted to mention about eval is that we had the luxury of almost kind of working with a structured output, but a lot of LLM or Gen AI applications, the outputs are very subjective. So you're not always going to have kind of clean-cut metrics like this, and you won't always be able to kind of rely on those out-of-the-box distance or entropy-based metrics. So here's kind of where a very popular technique, people call it kind of LLM as a judge or GPT judge, where you use a much larger, sometimes even proprietary model to actually do kind of the evaluation.
Yeah. And this is just wild. This is beautiful in some ways.
It is beautiful and also a little bit anxiety rising because you don't really have control over what's happening. But in this scenario, you'd pass in kind of your, let's say this fine-tuned LLM's output, and then you'll ask that larger judge LLM to basically assess the quality of it. And oftentimes people also add kind of a suggested answer or a golden answer to ask it to compare and rate between 1 through 5 and things like that. So either way, you want to have some strategy towards like quantifying the evals. Otherwise, you're just relying on sniff tests, and those fall apart pretty quickly.
Well, if you don't quantify it, then you're never going to automate it, right? Exactly. So that part is essential.
Exactly. Now we're finally at the last template where we get to serve our model that we've evaluated. So obviously there's a lot of different ways to serve these models. And before we talk about Ray Serve and all that, I just wanted to make it clear that we do have guides for how to use VLM or any other inference engine and use Ray Serve to be able to serve your models. But today, I'm actually going to demonstrate some of the Anyscale capabilities for serving these models using these inference engines, but also with a lot more features in terms of kind of doing multiple LoRa, tensor parallelism, more like production-grade features that our users are going to care about.
And just to explain that distinction, text generation, like TGI, VLLM, TensorRT-LLM, these handle the like single machine GPU performance, optimizing the inference engine on a single piece of hardware, right, or on a single machine. Whereas Ray Serve and Anyscale handle the multi-machine scaling, auto-scaling, scale to zero, all of these kinds of features, high availability, and all of the operational aspects around doing serving in production.
Exactly. Now, under our documentation on our website, we have a lot of different tutorials for serving more like traditional models to serving like deep learning, BERT-based models. Today, of course, we're going to focus on serving LLM models. Everything we're going to show today, you can create yourself configuration-wise, but we built a really kind of useful CLI for the service template. So I'm going to go ahead and run that just to show what it looks like.
I like how traditional models now refers to deep learning.
That's right. Things times have changed, Robert. So first thing it's going to ask you is kind of the model ID you want to serve. Here, obviously, there's a couple that we support out of the box, but you can really pass in any model from Hugging Face Hub, for example. And I'm going to go ahead and I believe we fine-tuned the Meta Llama 3 8B instruct. So I'm going to go ahead and paste that ID. And you're also going to, if you haven't already, it'll ask you for the Hugging Face token in case you need to have access to that. And GPU type here, I'm just going to choose A10 to serve this model. Tensor parallelism, I'm going to go with the default value here. Now, enable LoRa serving. So our fine-tuned model...
did 11 instead of 1.
Oh,
but
well, let's
do 11.
Let's do 11 here. Again, that's like the flexibility of what you want. And while this is a demo, I think we'll show kind of what that looks like. Nice. Enable LoRa serving. We fine-tune a model with LoRa, so we have those set of weights available. So I do want to say yes.
And while you're doing that, just want to point out, LoRa, of course, we talked about some of the advantages for fine-tuning in terms of training speed, but LoRa also has a lot of advantages for serving. In particular, if you have many different fine-tuned models that you want to serve. Yeah. Do you want to have a separate pool of GPUs for each of those models, or do you want to share the same base model and between all of the fine-tuned models and have a small number of adapters? And this is something we can enable you to do out of the box on Anyscale. It's really can be way more resource efficient.
Absolutely, yeah, extremely efficient here. And then obviously it'll ask for where those LoRa weights are. So I have our location here. I'm going to go ahead and paste that, and then it'll ask you the maximum number of replicas you want. So this is a demo here, so I'm going to not choose too many, but you're welcome to have as many different replicas as you want. I'm going to just keep it simple and have 2. And then it'll ask you if you want to further customize your config, and obviously you can do this later as well on your own. But these include things like tensor parallelism and other configs. I'll talk about a few other kind of changes that users may want to do at the end, but I'm going to say no here for now. And it'll give you the option to start it locally, so it'll just spin that up and we'll query it. I'm going to say no right now because I actually want to run it myself, so I'll go ahead and say no. So this created configuration under this file. This is just kind of a timestamp here, so let's look at one that I've already created. And you can see here that it basically has the LoRa path. It's got, if you've asked for any other kind of components here, it'll have that. And now we're ready to actually serve this. So what I'm going to do is serve the model locally, and all I have to do is kind of serve, run this one. Oops, I'm actually going to run this on the terminal here. Okay, so now this is actually going to kick off locally, following the configuration that we have. I believe we just did 2 replicas, so yes. It'll kick off 2 instances of the LoRa model that we have, and now we can actually query this. So I'm going to you can query this however you want. I'd like to kind of stick with the same kind of schema convention that we have from OpenAI. So I pass in a system content and a user content. And because in our model we have the chat template, we don't have to do this stuff manually. So we can just pass in text as we normally would, and all the templating, all of that will be done automatically under the hood.
So convenient.
Exactly. And again, I'm going to set temperature to 0, and I'm going to say stream true so we can see the outputs as they're coming. So now let's query this locally. You saw the inputs above. This is local, so I don't need to pass an actual key here, but we'll show that in action in a bit as well. But I just passed in one of the inputs from the data set and asked for it to generate the structured outputs. Yeah. All right, so now we're going to go ahead and actually run this call here. And you can see here, logs are on the right side, but you can see the output. And I think I actually printed the output as well, so that's why you see it twice. But looks like the right structured output that we're looking for.
Nice.
Awesome. So now to go to make this an actual production service, again, you can alter the configuration. Maybe locally when you're testing, you did 2 replicas, but maybe in production you want 200. You can play with the configurations, and to go to production, all we have to do is actually deploy the service. Yeah. So with Anyscale, we have a command to use the same configuration and deploy it. And when you run a service like this on a workspace, you get a little modal down here that says, the service, the name of the service is deployed, and you can go ahead and click to view the service. Or from our Anyscale dashboard, you can go over to Home and Services, and you'll see it as well. But this will take you directly to our main central dashboard for the service. You can see it's still spinning up right now. But here, anytime you or anybody ever makes a request for this service here, you'll see kind of the QPS, any errors that are coming up, the kind of latency numbers as well. And one of my favorite parts is the full logs. And I can, kind of do it by component, the log severity level, time period, and even regular expressions here as well.
Nice. That's fantastic.
So let's go ahead and actually send a quick request here. So the neat part about the service here is that up top, I have a little query button. And here I have information about like the actual URL that it's running in. So I'm going to go ahead and copy that. Obviously, you can curl this command as well. We've done it locally so far. So now I'm going to, we filled in these credentials using the kind of the query instructions from here. So replace the URL and the special token as well. And now I'm going to use the same query function to now pass in these credentials instead. And we can see the output is the same and it's the correct output.
Nice.
All right, Robert. So now we've seen all 4 workloads together, and any kind of big takeaways?
Well, it's just amazing to me. Typically, if you go back before Ray or before Anyscale, each of these different boxes would have been a different framework or a different distributed system. The fact that you can handle the data workloads, handle the training workloads, handle the serving workloads, evaluation, all in the same framework, in the same system, that's mind-blowing to me.
Mm-hmm. Yeah, and it didn't have to change context at all.
Yeah. You're writing Python code.
Exactly. And there are obviously actually many things we haven't had a chance to show yet that hopefully our users find through documentation and future webinars. But each of these things have been completely isolated and can be combined or be kind of stay separate. And we can launch kind of production versions of all of these. And for example, we took our model that we served locally and we went to production with one line. And we went to production in a very highly scalable and reliable manner. We could have done the same for the other workloads as well. For example, our data preprocessing step or our model fine-tuning aspect. Yeah. Those, again, also one line to take that script that does that said workload and run it as an Anyscale job. These are kind of isolated workloads that people could execute manually, attach webhooks to happen on certain kind of actions. Mm-hmm. And it's just a great way to kind of create great CI/CD workflow around all these.
Yeah, I mean, I think for someone just casually watching this, it may have just felt like writing Python code on your laptop. It feels like just developing in a notebook or developing in VS Code. But whatever resources you need, when you needed a GPU for training or multiple GPUs, they were there. Mm-hmm. When you needed a larger cluster for the data processing, it's there. Mm-hmm. And when you don't need them, they're gone. Exactly. Right? Like the fact that you can really enable people who know how to program in Python to do all of these workloads at scale without needing to learn about the scheduling and the fault tolerance and the distributed systems, that's, to me, one of the most impressive parts.
Exactly. And I didn't have to make any compromises on the tools that I could use. So, coming from kind of a local laptop world to running large workloads now, still get to use my favorite tools, both from the IDE standpoint, but also specific libraries, PyTorch, Hugging Face, integrations with great tools as well. I kind of bring in my world of machine learning and be able to run these same workloads at a very large scale.
Absolutely, and you showcase this, but open source is really the foundation of the AI ecosystem. You mentioned PyTorch, of course, and DeepSpeed and VLLM and Ray and all of these different tools, and these are Hugging Face, and these are really work together to make AI possible.
Awesome, Robert. So we just went through this, but how can our users actually get started with this and then start to use it for their own applications?
That's a great question. So Goku put together these fantastic notebooks, and now I personally want to try them out. So what anyone watching can do is they can go to Anyscale.com, and on Anyscale.com there's going to be a button that says try this out. And what you're going to have to do is click on that button, and you'll have access to everything that Goku just showed you. So you'll be able to do the data prep, you'll be able to fine-tune the models, deploy the models, do evaluation. We have templates for everything, so it's going to be fantastic.
And this was a pretty lean tutorial where we weren't really using too large of data sets, but it still involves kind of training models and stuff. Do users get some kind of free credit?
Yeah, there are free credits to get started and try things out.
Hopefully our users found all this useful, and we look forward to sharing more capabilities in the future.
Yeah, lots more to come.